Okay, so very good. All right, so let's just finish this section on chain rule. We're almost finished with that. So, and then if you have questions or whatever about this midterm, we can discuss. So this is chain rule. So we are continuing now. So now this is more or less the general case. So the general case is we have a function of several variables, f of say x1, x2, xn, function of n variables, and each of those variables are functions of n variables, where with xi equal to gi of y1, y2, yn, right? So you replace in this function xi by the y corresponding y values, and then you get a function of n variables all of a sudden. So this gives you f of, say, g1 of y1, ym, g2 of y1, ym, and then gm of y1, ym. Now, mind you, these are not powers, right? These are just labels, just to refer to different functions. These guys are not powers, right? And what we want to know, we want to find, so this, we call it f of y1, y2, ym, right? It's a function of n variables now. And what we want to find is partial derivative of capital F with respect to y1, y2, yn, right? So the desired is to calculate partial of F with respect to y1, for example. Partial of F with respect to y2, and partial of F with respect to ym, right? So let's write one by one each of these cases, and then we'll see what is the pattern. So for example, df partial of F with respect to y1. So here is a function of m variables y1, y2, ym, and we want to compute partial with respect to y. So the name of the game is like this. You take partial of this with respect to x1, you multiply to partial of x1 with respect to y. And then with respect to x2, x2 to y1 again, and so on. So for example, this one is going to be df dx1 times dx1 dy1 plus df dx2 dx2 dy1, and so on. You go on, and the of course not so on, plus df dxn dyn. I mean, I could have avoided even using this G1, G2, Gm variables. So I'm just using these guys as functions of y1, y2, yms. But if you want, you can replace these things by y1, for example, if you want, but it's understood. I mean, this is kind of easier to remember because there is this x1 top, x1 bottom, cancel. Top down, cancel, and then you get kind of very systematic kind of, there's some pattern you can see. I mean, this is, remember, is G1, this is G2, this is GM. But I definitely don't recommend remembering in that form. I recommend remembering in this form. This would be very easy to remember. Is that what you want to say?
Yeah. So for the last like del ym, should it be del y1?
Oh, del y1, absolutely right. All of a sudden, where is y1 came from? Thank you. Yeah, exactly. Okay, so that's it. And then df dy2. We just write the same df dx1, dx1, oh, dy2, of course. dy2 plus df dx2, dx2 dy2 plus df dxn, dxn dy2. And for the last one also, so of course, you just continue, and then the last one, df dym is equal to df dx1, dx1 dym, plus all the way up to df dxn, dxn dyn. So this is the general case. We have a function like from Rn, n variables going into, yeah, I mean, so we have this function from Rn to R, and here I have a function from Rn to Rn, and then we compose these two, and then we are saying that indeed this the partial derivative of this composition is obtained by these mixed partials here, and not mixed partials, these partial derivatives here times corresponding partial derivatives there, according to this pattern. So there is a kind of bit more graphical explanation of this in your book in terms of trees. So you have branches, and then at the end of each branch, there are several branches again, spreading out, and then you take all the products and sum over all those products. But I don't emphasize that here because I think this is quite clear, easy to remember. So this is very general. Of course, now we need some examples so that you feel comfortable applying this rule. Before doing example, let me give you a little more theory of this things, partial derivatives, and then any question or questions? Okay, it looks like there are no questions. Okay, so now there is something called implicit differentiation. Implicit yes. Again, you can recall from one variable calculus what was the rule. So this was the one variable case, recall. We have a function like this, a relation between x and y, a functional relation between x and y like that, equal to 0. So from here, we imagine y is a function of x somehow, right? You can imagine for a given x, Well, this is an equation for y, and then you can solve it for y, and then find the value of y in terms of x, in good cases, right? So then the question was, what is dy dx, right? That was the issue, right? And we were told in one variable calculus to do this, we just take derivative of this guy with respect to x, right? We just get, okay, so this is, so this, we just write df dx, right? Df dx plus df dy times dy dx. Right? And this is equal to 0. Because this guy is identically equal to 0, so if you take its derivative with respect to x, it's also 0. It's just a constant function 0, right? So you just put that equal to 0, you get that. So here then you can solve dy dx. I guess you have seen this in one variable calculus, right? Or maybe not, because it needs partial derivatives. You didn't see that, right? Did you? No. Okay, so this is new, right? So one variable case. Okay, so yeah, this is new. Sorry. So this is equal to minus. Now you just divide df dx over df dy negative fx divided by fy. Yeah, because I just thought, how could you have been given this formula? Because you didn't know about, we're not supposed to discuss partial derivatives in one variable calculus. So, but I somehow remember there was something about that.
Yeah, we talked about it, but we didn't use partial derivatives.
How did you do that?
We took the chain rule, I believe, somehow.
How can you?
I don't know what.
Okay, so yeah, I think there was implicit differentiation. So there was some context. So partial derivatives is absolutely no in that course. I agree. I mean, okay. Anyhow, so this is dy dx equal to negative fx over fy. Okay, so of course, I mean, this is given under a condition, right? What is the condition to do this? You have to be able to divide by df dy. If this is 0 at some point, you cannot divide, then we are in trouble. Okay, so here is an example. Find slope of the curve defined by the equation okay, so this equation is y5 plus x y2 plus x equal to 1 at x equal to 0. Right. All right, very good. I like that. Okay, so there is an equation. Okay, so this is first of all, so you understand the question, right? Any question about the meaning of the question? So what this question is asking? The question says, well, there is a relation between y and x. So for each x, at least for x near 0, we are supposed to find the value of y by solving this equation, which is almost an impossible task because it's a fifth-degree equation. But no matter what, let's assume there is a solution. Let's assume. And then once you have the solution, then you're supposed to find the slope of this curve, meaning the derivative of the curve, right, at that point. So that's the meaning of this question. Okay, first of all, so x equal to 0. So here is 0. And so there is some curve passing somewhere. So that at some point, so this point, we don't know which point is it, but then we have to find the slope. So this is y equal to y of x. Is the question clear now? Or a little more clear? I hope. Yeah, oh, very good. So now, so one task is to find what this y point is. Well, let's put x equal to 0, see what is the value of y. Question? Okay, so let x equal to 0 in this equation, then you get, well, y5 equal to 1. What is the solution of y5 equal to 1? There's only one solution, 1. There is no other solution for us because we live in real world, not in complex world. So 1 equal to 1. Okay, so this point is 1. And we want to find the derivative of this function dy dx at x equal to 1. So that's the question. That's the intent of this question. Right? That's what we want to do. Okay, then the only way to proceed would be to use implicit derivatives, right? Now, one question you may you may complain about is, one issue is this is equal to 1, but here I said this is equal to 0. But that doesn't matter. You just bring this 1 to the left-hand side. This would be your f of x and y. That's completely a cosmetic change. That's not important at all. Okay, so then with that understood, let's now compute. So this equation now, I just take derivative with respect to x. You can memorize the formula, but so, okay, so let me just, because I just derived it, I still remember it. So y prime of x is equal to minus d of dx, fx over fy, at x equal to 1, right? Where f of x and y is equal to this guy, minus that. Okay, so that's equal to negative. What is fx? What is the derivative of this guy with respect to x? It's with respect to x, of course, is y2 plus 1, right? It's y2 plus 1. What is the derivative with respect to y? This derivative with respect to y is 5 by 4 plus 2xy, right? Plus 2xy. And all of this I have to calculate, we have to calculate at x equal to 1. X equal to 0 rather, and y equal to 1. Well, that's easy because that's equal to negative. Y equal to 1, this is 2, 5. That's negative 2/5. So actually, this curve, as it passes through this point, it's going downward. It's not going upward. Its derivative is negative. So, and this is not quite right for me to do it like that. So I just say, okay, negative 2/5. Right. So that's a good question, I would say, because it kind of tests our understandings. Now we can also do implicit, mixed or implicit partial derivatives. So that's any question about this, by the way? Everything clear? Okay, good. So now let's do implicit partial derivatives. So, so a function like this is given. For example, is given something like this: f of x, y, and z, and equal to 0. And we want to find the z dx and the z dy. We want to know these things. So what is the idea in this case? The idea in this case is that, okay, so this is not 2 variable. This is 3 variable here, right? So z is a function of x and y. So this definitely you didn't do in 1 variable. I'm pretty sure about that. Because this z is a function of x and y. You didn't have that case. All right, so z is a function of x and y. We have that. So then this is a legit question. What is the z dx? What is the z dy? Right? That just makes sense to us. All right. So we just use the same method. Just say, okay, df dx plus dx times, I would say, times. You just for yourself write this, but then you can forget about this. You can plus df dy dx plus df dz dx equal to 0. Yeah, I recommend you write it like this first, because what is it? We are taking derivative of this guy with respect to x, and you get this equation by chain rule, right? So chain rule gives me this. Now, x and y are independent variables, z is dependent variable. That's the thing. So because x and y are independent variables, anyhow, this dx is 1, but dy dx is 0, and dz dx is what we want. So we get dz dx is equal to negative, df dx over df dz. So that's negative fx over fz. It also works at a very formal level. You can cancel df, and then this becomes dz dx. If you can check you haven't made any blunders here by just doing, just canceling f's, df's, and then you have dz dx using rules of fractions, quotient rules of fractions. All right, so and also dz dy in a similar fashion, we can say dz dy also dz dy minus, we just say fy minus yx. I didn't write same thing. I mean, you just write the same thing, but this time with respect to y, and then. So, any questions? Yes.
Why is dy dx 0?
Oh, dy dx is 0, right. So why dy dx is 0? Because we are treating, in this case, y and x as independent variables. So there is no dependence of y and x. But z is the dependent variable. Z depends on x and y. But here, they don't, I mean, so this is like in xy plane, x can go any direction, y can go any direction. There's no dependence between. So that's why. This is a bit of formal reasoning, though. I mean, it's not an absolutely correct answer, I should say. I'm just telling you that Yeah, I mean, the correct answer is that I have to prove this result. And once I prove it, then you'll see. Then you know. But you also sense that there is some logic to this argument that x and y are independent variables. So if you want to take derivative of that, there's no dependence, so it's zero. But I don't like this argument, to be honest, myself. So it's a bit of kind of cheap answer. Sorry about that. I mean, I have to prove this. I'm not proving any of these results for you. I'm just working like a cook now, just giving you recipes to apply. And to be honest, at first it's important to know the techniques so that you gain facility with techniques, and then we can try to prove this or that. I mean, I've been proving some results to some extent, but then, you know, if proofs go too difficult, there's always a question, is it going to be an exam? And there's always the answer that no. And then there's always the comment that why then? So things like that. So I try to kind of balance the amount of proof with non-proofs. But knowing the kind of gimmicks of this, or sort of yoga of these rules, is very, very important. You have to gain facility with these things. I mean, for example, if you do physics, I don't know if you're doing physics. I mean, in thermodynamics, this idea is kind of very, very fundamental. I mean, you do this in thermodynamics all the time, and in that case, they are called Maxwell's rules. So now let me prove a result which is actually similar to that, but it's kind of interesting. So this example, given a function, given a relation of x, y, z equal to 0 between three variables x, y, z, find df dx. Oh, sorry. Find dx dy times dy dz times dz dx. Okay. So that's the question. Dx dy times dy dz times dz dx. Of course, I mean, the first thing is to understand what we are asked. I mean, what's the intent of this problem? What is it that we're looking for? That's very, very important to ask and to understand what's the meaning of the question, and then try to solve the question. So what is the meaning of this problem? The meaning is that, I mean, it's just written, I mean, by the way, these are products, right? Times that. It's just written that, like that, but there is a kind of implicit understanding in what we are doing here. What is the implicit understanding here? What is the underlying rule here? The underlying rule here is that when you write dx dy, it means that you're taking x as your dependent variable as a function of y and z. But here now, you're thinking of y as a function of z and x, and here you're thinking of z as a function of x and y. So this is like three games in one game. You're doing it, you know, because I mean we are playing, we are thinking of these variables as totally differently each case. Here x is a function of y and z. Here y is a function of z and x, and here z is a function of x and y. That's the only way we can think of this, right? And so the question is, what is this value? Oh, there was a question, good, in the chat. So chat is working, that's good. Okay, so I got an answer, yes, that's the correct answer. Yes, so very good. So, but the question is why? Aidan, did you see this in your thermodynamics course? Not yet, you will see it. They are called Maxwell's rules, yeah. Okay, the answer is equal to -1. So this is quite surprising, right? Because so far I've been advising you to cancel these things as a check, and then okay, so but this check doesn't work in this case. See, this is check. You get 1, you don't get -1. So there is something to that rule. I mean, there are some limits to that rule, right? So proof. You just have to use this rule 3 times with different variables. So let me call this a star. Just use a star 3 times. So what do I mean? I mean, okay, star tells me that dx dy equal to negative. Well, what is this? Negative, what is dx dy? Fy over fx, right? Negative Fy over fx. This is Fy over fx. Right? And, okay, divide dz, negative, well, this time is going to be dx dy is Fy. This is fz over Fy. Right? This is fz over Fy. And similarly, here, dz dx negative. Now this is fx over fz. So we have 3 relations. Now we have to multiply these 3 relations because what we want to do is multiply these 3 relations. Then we get dx dy times dy dz times dz dx is equal to -1 times Fy over Fx times -1 Fz over Fy times -1 Fx over Fz. And then now, these are legitimate fractions. These are not phony fractions like here. These are really fractions. This is a fraction of this derivative by that derivative. These are not phony. Here is a bit of, I mean, it's not totally phony though. I mean, there is something here, but these are not fractions, right? I mean, derivative dy dx is not a quotient of 2 quantities. It's the limit of quotients, but here is really quotient. So I can cancel. So we can cancel this by that, this by that, this by that, but -1s remain, and then you get -1 times -1 times -1. Right. So that's very good. So we have this. So the whole thing is to realize, like in these applications of this sort of partial derivatives and implicit partial derivatives, is to realize what quantity is a function of what other quantities. That's all we have to understand. What are your variables? What are your functions? Or what are your dependent? What are your independent variables? If you understand that, then there's no way you can make mistakes by this applying this. Any questions or comments? Okay. So that we covered. I think we basically covered different aspects of chain rule. There are a couple of things about partial differential equations. I gave one example of partial differential equation, but then there are other examples that it's in your book, so I want to discuss. That's, I believe, in section 4.4, I guess, or maybe 4.3. So recall we discussed partial differential equations. So one equation we discussed, you remember, was Laplace equation, right? Laplace equation. Laplace, by the way, is that famous French mathematician, astronomer, scientist, one of the greatest of all time, who wrote this very amazing book about astronomy and calculated orbits of stars. And it's an amazing volume. It's incredible. So the story is that Napoleon was a very interesting character, right? I mean, he looked at the book, he was quite impressed, but he said that, but sir, in your book, I didn't see any reference to God. All these things. Laplace said, I didn't need that hypothesis. so this goes a long way to even current debates in France, I guess. So yeah, anyhow, so I guess that's an interesting thing about dialogue between Laplace and Napoleon. So this Laplace, his name is attached to many equations, many results in math, physics, probability theory, a lot of things. Anyhow, so this Laplace equation is delta U equal to 0. Well, delta U is equal to UXX, for example. And you say in 3D, UXX plus UYY plus UZZ, which is, of course, D2U dx2 plus D2U y2 plus D2U z2, right? Now equal to 0. This is Laplace equation. And you remember what we call the solution of Laplace equation? Such functions were called. You remember what we call those functions? Yes. Harmonic functions, exactly. So we say U is harmonic. Probably even this name was coined by Laplace himself. He didn't want to call it Laplace functions. Anyhow, so we have these harmonic functions, and then there is so this already we discussed, right? So now today there is one equation which is wave equation. It's a very famous equation. So today we have this wave equation. Right. So what is wave equation? Have you come across wave equation by any chance? Or? So the equation is UXX. I mean, I would say UTT equal to C squared UXX. So what is this equation? C is a constant. C is a constant. It's basically, it turns out to be C is the speed of the wave. The speed of the wave. Okay, so that's this one. So what's the meaning of this equation, and what is it trying to tell us? See, the equation, you have to understand U. So U, your unknown, is a function of T and X, of course, right? U is a function of T and X. So what this U says, U is the kind of amplitude of the wave at point X and time T, right? At point X and time T. So here is what this guy discovered, is that, so imagine you have some wave motion going on the line. But then this is the amplitude. So this is your U of 2 and T and X. So this is your x-axis, and time axis I don't draw. Time axis is some other axis that I don't draw. But U depends on T and X both, right? So this quantity tells us what is the height of your wave at time T. And this height, of course, changes, because when you go to seashore, you see that, the wave, the river, anywhere, your bathtub, whatever. You look at waves, and of course, at each point, it's going up and down, up and down, up and down. If you look at just one point and study the variation of wave at that point, you get this height, depending as a function of time. So this is what is this equation. I'm not going to drive it. Maybe in physics courses we'll drive this, but this is the thing. So, but this is in 1 plus 1D. Plus 1 dimension. Now, there is a kind of nice solution for this wave equation, which I'm going to write down, and you'll see. So here's this, show that for any function, but any, I really don't mean any function, I mean any reasonable differentiable, at least twice differentiable function. That's what this issue is not a big issue for us. For any, I just say function U Tx, so a little bit like this, f of x, the function U Tx equal to f of x plus ct is a solution of the wave equation. So this is quite remarkable, right? You're saying that take any function, whatever you want, as long as it's differentiable is okay. It's smooth enough is okay. Then form this new function u of t and x, which is f of x plus ct. Because here f is a function of one variable, here you're creating a function of two variables, because in wave equation we need two variables, according to this simple recipe, x plus ct, right? And we are saying that this is always a solution of the wave equation. So remember, the wave equation was, so let me just go here and solve it here. So I have to show UTX satisfies UTT equal to C squared UXX. Well, let me do that. So this C is exactly the same C. Just kidding. Okay, well, what is UT? Can you tell me what is the derivative of this guy with respect to T? Well, of course, I mean, we have to use chain rule, right? Because this is a function of one variable, and that variable is a function of, so this is equal to x plus ct with respect to t times f prime at x plus ct. I keep writing in different ways. It's awful. Okay, so that's equal to that. So that's equal to c f prime of x plus ct. Okay, well, what is UTT? We have to do it again. This is equal to C times C times F double prime of X plus CT. That's equal to C2 F double prime of X plus CT. Right. So now, what is, so we have to compute UXX also. But UXX is also very easy. UX is just f prime at x plus ct, and uxx is equal to f double prime at x plus ct. Okay, of course you see that comparing this 2 with 1, compare 1 and 2, you get that indeed we just verified that UTT equal to C2. So satisfy this partial differential equation. There was a chat question. Sorry about that. Oh yeah, of course. Yeah, this was a long time ago. Yeah, thanks, Aidan. Yeah, excellent. Very good job. Yeah. Excellent. So, although I don't know who exactly coined the term harmonic. It was not Laplace, I don't think. So, but the question is, what is the meaning of this calculation we did here? We'll discuss that later, after midterm. We'll discuss it, I think. I think there's a very nice meaning. It just means that you take one constant function, you move it with a speed c, backward in this case, you create a wave. And some waves are created like this. And then, yeah, okay, so there is some discussion about these things later on. We can discuss. Okay, I think we are done. So I'm here. If you have any questions, let me know. I mean, I'll just stop the video now. So for that.